Machine learning is applied philosophy. It is the ancient question of how we learn, made empirical and turned into code. This is a full course on machine learning, explained through real philosophy with real citations. How can we learn anything? Plato asked that in the Meno. Can we justify induction? Hume said no. Neural networks are Aristotle's associationism made literal. Overfitting is Plato's cave. Generalization is Kant's categories. Loss functions are Bentham and Aristotle arguing about the good. Language models are Wittgenstein's language games. The Chinese room is Searle's challenge to everything. 16 chapters covering induction, Bayes, neural networks, gradient descent, overfitting, generalization, loss functions, reinforcement learning, language models, consciousness, and ethics. By the end, you will understand both machine learning and the human mind better. How can we learn anything at all? Plato posed this paradox in the Meno around 380 BC. If you do not know something, how can you recognize it when you find it? And if you do know it, why search? Plato's answer was that all learning is recollection, because the soul already contains the forms. Modern machine learning answers differently. The model does not know the answer in advance. It learns from examples, thousands and millions of them. No innate forms, no recollection, just data and statistics. But the paradox survives. A model that has never seen a cat cannot recognize a cat. It must be shown. The Meno paradox is the philosophical origin of training data. You cannot learn what you have no examples of. That is not a technical limitation. It is a logical one. The deepest problem in machine learning was identified by David Hume in 1748 in his inquiry concerning human understanding. Hume asked how we can justify the assumption that the future resembles the past. Every time you have seen the sun rise, it has risen. But that is not proof it will rise tomorrow. You cannot justify induction without using induction, which is circular. Hume called this the problem of induction, and no one has solved it. Machine learning runs on this unsolved problem. Every model predicts the future from the past. Every training set assumes the test set will look like the training set. When a model fails, it is usually because reality broke the assumption. Hume predicted machine learning's failures 300 years before the first neural network. Bayes' theorem is doubt made mathematical. Thomas Bayes published it posthumously in 1763, and it answers one question. How should beliefs change when new evidence arrives? Before the evidence, you have a prior. After the evidence, you have a posterior. The formula updates the first into the second. Hume himself used a version of this logic in his famous essay on miracles, arguing that a miracle claim is only rational if the evidence for it outweighs the prior improbability. Machine learning is Bayes at scale. Spam filters update the probability that an email is spam. Recommendation systems update what you might like. Every time a model changes its mind, it is doing Bayesian inference. The algorithm is not a computer invention. It is the formalization of rational belief. Neural networks are Aristotle made literal. In his works on memory, Aristotle argued that recollection works by association. Ideas are linked to similar ideas, to opposites, and to things experienced together. Hebb's rule, stated by Donald Hebb in 1949, is the same insight in one sentence. Neurons that fire together wire together. A neural network is exactly this. Thousands of artificial neurons, connected by weights, and the weights change with experience. When the network sees a cat and a label that says cat, the connections that produce the correct answer grow stronger. Aristotle described the mechanism in 350 BC. Hebb stated it in 1949, and now it runs on your phone, recognizing your face. Associationism was dismissed as naive. It turned out to be the foundation of intelligence. Gradient descent is the philosophy of water. Laozi, in the Tao Te Ching, wrote that water benefits all things and does not compete. It flows to the lowest places, and yet nothing is stronger than water. Gradient descent does the same thing. The model defines a landscape where height is error. Then it computes the gradient, the direction of steepest descent, and takes a step downhill. Repeat until it reaches the valley, the minimum error. No intelligence is needed. No plan. Just follow the slope. Laozi taught that the sage acts without forcing, and gradient descent is action without forcing. It does not try to solve the problem directly. It lets the landscape guide it downward. The deepest philosophical insight of machine learning is that intelligence can be pure descent. Wisdom is just water finding the valley. Overfitting is the allegory of the cave. In Book 7 of the Republic, Plato describes prisoners chained in a cave, watching shadows on the wall. They believe the shadows are reality. A prisoner who escapes sees the real world, the forms, and can never mistake shadows again. An overfit model is a prisoner who has memorized the shadows perfectly. It has learned the training data so well that it has learned its noise, its accidents, its shadows. It scores perfectly on the training set and fails on anything new. The cure is older than computing. Occam's razor, from the 14th century, says prefer the simpler explanation. Regularization is Occam's razor implemented as math. Penalize complexity. Prefer the model that explains the data with the fewest assumptions. Generalization is escaping the cave. How does a model know anything about the world it never saw? Immanuel Kant, in his Critique of Pure Reason, argued that the mind is not a blank slate. It comes with categories, space, time, causality, that shape all experience. You never see causality. You see events and infer cause through the category of cause. Kant called this the a priori, the structure that precedes experience. Machine learning has the same idea under a different name. Inductive bias, the set of assumptions baked into the model before training. A neural network assumes smoothness. A decision tree assumes boundaries. These assumptions are the model's Kantian categories. Without them, learning is impossible. The model is not a blank slate. It is a structured mind, and that structure determines what it can learn. Every machine learning model optimizes a loss function, and a loss function is a moral philosophy. Bentham's utilitarianism says the good is pleasure and the bad is pain, and the best action maximizes the balance. A regression loss function says the good is small error, and the best model minimizes it. But Aristotle, in the Nicomachean Ethics, rejected simple calculation. He argued the good is eudaimonia, flourishing, which cannot be reduced to one number. This is the modern debate about AI. What should the loss function be? Minimize cost? Maximize engagement? Preserve privacy? Every choice encodes a philosophy of the good. When a social media algorithm optimizes engagement, it is Bentham in production. When researchers argue the objective should be human flourishing, they are Aristotle. You cannot escape this. Every metric is a moral claim. Reinforcement learning is Skinner's box at scale. F. Skinner showed that behavior is shaped by consequences. Reward the behavior and it strengthens. Punish it and it weakens. Operant conditioning, he called it. And he believed free will was an illusion. Reinforcement learning is operant conditioning formalized. An agent takes actions, receives rewards, and updates its policy to maximize total reward over time. The Stoics would recognize the method. You become what you practice, and every action writes a habit. AlphaGo became the greatest Go player in history not by being told the rules of mastery, but by playing millions of games and keeping what worked. Skinner's claim that there is no ghost in the machine is the operating assumption of modern AI. The behavior is the intelligence. Large language models vindicate Wittgenstein. In his Philosophical Investigations, published in 1953, Wittgenstein argued that the meaning of a word is its use in the language. He called these context language games. Words do not refer to hidden essences. They are tools for getting things done in social situations. Language models learn exactly this way. They are trained on billions of sentences, and they learn to predict what word comes next. They never see definitions. They never see a dictionary. They learn use. And somehow, meaning emerges. A model that has never been told what love means can write about love because it has absorbed the language game. Wittgenstein argued this is all meaning is. A language model is the strongest empirical evidence ever collected for the philosophy of ordinary language. Can a machine understand? John Searle's Chinese room argument, from 1980, says no. Imagine a person in a room with a rulebook. Chinese symbols come in, and the rulebook says which symbols to push out. From outside, the room appears to understand Chinese. Inside, there is no understanding, only symbol manipulation. Searle argued that computers are the Chinese room. They manipulate syntax, but never reach semantics. They never grasp meaning. The strongest reply comes from the system's reply. The person in the room is one part of a system, and the whole system understands, even if the part does not. This debate is unresolved, and it is Descartes' mind-body problem in modern form. Is understanding an inner state or a behavior? Large language models have made this ancient debate the most important question in technology. Intelligence emerges from parts that are not intelligent. Aristotle said it first in the Metaphysics. The whole is greater than the sum of its parts. A single neuron knows nothing. 100 billion of them produce consciousness. A single parameter in a language model knows nothing. 1 trillion of them produce poetry. This is emergence, and it is the central mystery of machine learning. No one designed the ability to reason into GPT. It emerged from scale, from pattern, from the statistics of enormous data. Reductionism says explain the whole by the parts. Emergence says the parts are necessary but not sufficient. The ancients knew this. Aristotle watched a city, made of individuals, produce culture that no individual planned. Machine learning has made emergence an engineering fact. The whole really is greater than the sum of its parts. If machines can think, what is consciousness? David Chalmers named the hard problem in 1995. Why does information processing feel like anything at all? Descartes split mind from matter in his Meditations, arguing that thought is a substance that cannot be reduced to extension. Gilbert Ryle mocked this as the ghost in the machine. Machine learning has revived the debate with urgency. A model can pass tests, generate text, maybe someday pass the Turing test. But does it feel? The hard problem is not about behavior. It is about experience. A philosopher who asks why the sun rises would say the model's training, like the sunrise, is the cause. But why does any of it feel like something? Chalmers says we have no idea. Neither does anyone else. Consciousness remains the one thing machine learning cannot yet touch. Ethics of AI is Kant's categorical imperative in production. In his groundwork of the metaphysics of morals, Kant argued that you must treat humanity, in yourself and others, always as an end, never merely as a means. Modern AI ethics is this sentence operationalized. Recommendation algorithms that maximize engagement treat users as means to attention. Surveillance systems that predict crime treat people as data points. The categorical imperative asks, would you want every system to behave this way? Kant's test is the universalizability test, and it is the closest thing we have to an alignment principle. When researchers talk about aligning AI with human values, they are doing moral philosophy. The alignment problem is Kant's problem. What does it mean to respect persons? Machines will not answer it. Only philosophers can. So what does machine learning teach us? It teaches us that we are machines, and that we are not. Hume was right that induction is unprovable, and yet every model proves it works anyway. Plato was right that learning needs examples, and the Meno paradox lives in every dataset. Wittgenstein was right that meaning is use, and the language models are his evidence. Machine learning is not just technology. It is philosophy made empirical. We built machines that learn, and in doing so, we discovered how we learn. Every breakthrough in AI is a footnote to an old philosopher, and every old philosopher is waiting for the next breakthrough to prove them right or wrong. The mirror of machines shows us ourselves, in sharper detail than any philosopher could have imagined.